Hey kiddos, so today we're going to be talking about substitution. Essentially what substitution is it's solving the same types of problems that we were solving when we were doing graphing, but it's doing it without the graphing aspect of it. So we're still solving a system, we're still finding a solution to a system, finding a point that is going to work for both equations in the system, but we're doing so without the graphing aspect of solving systems. So still, when I think of systems, I like to think about it this way. We have two locked doors, and we're basically looking for a key that is going to unlock both of those doors. Okay, that's what that point of intersection is. The point of intersection is the one point that is going to make both equations in the system work. Okay, so today we're going to be doing that without the graphing aspect of it. So let me see if I can actually hit the slide that I want to. Okay, so again, a reminder, solving a system means we're finding a point, and a point is written as x comma y, so we need two values. That makes both equations true or both equations work. So when I plug in that point, when I plug in the values of x and y into both equations, it's going to make both equations true. And that's essentially what I'm looking for. That's what I mean when I say I'm looking for a key that unlocks both doors. Okay? Now, what we're going to be doing today is going to solve the system, but again, we're using substitution, which is our new method, and we're going to use substitution whenever we encounter a problem where no graph is provided to us, where the equations are too difficult to graph, meaning that they're not presented to us in either y equals mx plus b or in a standard form that easily divide so that we can use the x and y intercepts. So usually substitution is used when you don't want to manipulate the equations so that you get slope-intercept form. Okay? Very easy to use substitution, in particular when one of the equations either says y equals or x equals. Okay, now we are going to be using very simple and very straightforward substitution today. We're not going to have to manipulate any equations. We're not going to really have to do anything too crazy. Most of our problems today are already solved for y equals so that they easily can substitute into the other equations. Now just know that substitution definitely gets more complex than this, but we're only focusing on this one aspect, this one type of substitution problem, because this is the problem that we're going to be encountering very soon. So we're going to specifically focus on these types of problems where y is already solved for, and we're using that to solve for the other variable. Okay, here's our process. Now, these notes are already provided to you. If you look in the daily agenda, the notes are already linked in for you. So I'm not going to go over these steps too independently. I'd rather do that while we go through the problem. So just know that these are in your notes already. And as I go through each example, I'll be talking about the steps. Okay, here's our first example. So on a problem like this, the first thing you want to do is look at both of your equations. We notice right away that our first equation, y equals 4, is already solved for us in terms of what y equals. So when we have y equals 4, that's very important, very useful, because I already know one of the values that I'm looking for. Remember, I'm looking for a point here. So I need an x value and a y value, and I already have a y value. So I can go in down here, and I can write that in. The y value is 4, the y value is 4. Okay. Now what I want to do next is actually the substitution process. So because I know y equals 4, I can plug that y value in right here, change that y value into a 4, and then I will only have one variable in the bottom equation. So I'm going to keep everything in the bottom equation the same. So I have 3x. I'm going to add 2, but instead of putting a y, I'm going to just put parentheses there for right now, equals 29. Okay. And now in that parentheses, I'm going to write the value that I have for y, because y is being substituted for the value that it is, which is 4. Okay. And now I can go through and I can simplify this. So I have 3x plus 2 times 4 is going to give me 8 equals 29. And now what I have here is a two-step equation that I can super easily solve by working backwards. I'm going to subtract 8 from both sides. Our 3x comes down. The positive 8 and negative 8 cancel out. 29 take away 8 is going to give us positive 21. And now I'm going to divide both sides by 3. That's going to isolate x on the left-hand side. So x is by itself, which is what I want, equals 21 divided by 3 is going to give me positive 7. And now I have my second value. So I have a value for x and I have a value for y. So x is equal to 7. And then I can write that in the ordered pair as well. Now what that means is if I were to graph the original equations, y equals 4 and 3x plus 2y equals 29, if I were to go and graph those, this is the point of intersection that I would get. This is where those two lines would cross over. Okay. Now we're going to make this a little more difficult. We are going to now increase the complexity of what y is equal to. So in this problem, we also have y equal to something. So the difference is that y is not equal to just an integer. Y is equal to 2x. This means that eventually I'm going to have to come back to this value because I don't have an actual value for y yet. I have y equals 2x. I am still going to follow the same procedures. I'm going to take that y and I'm going to substitute that in to the top equation. So the top equation is then going to become 20x minus 7. And then again, instead of the y, I'm going to put a parentheses in, equals 18. Okay. In that parentheses, I'm going to go ahead and substitute the value of y, which is 2x. And again, the reason I'm doing this is because now my equation only has one variable. It doesn't have x's and y's, it only has x's now. So I'm going to go ahead and simplify. 20x is going to stay the same. Negative 7 times 2x is negative 14x. And that is equal to 18. Now what I have to do is I have to simplify by combining like terms. 20x take away 14x is going to give us 6x, positive because 20 is bigger, and that's equal to 18. And now I have a one-step equation that I can super easily solve by dividing both sides by 6. The 6's cancel out, so x is isolated. That's what I want. X is equal, 18 divided by 6 is going to give us 3. So I have one value now. X is equal to 3. Okay, I can write that in my ordered pair. Now to go back and solve for y, what I'm going to do is I'm going to take that x value and go back to my cloud that I made in the beginning. We'll say that's a cloud. And we're going to substitute that in for the x value. So y equals 2, and then I don't want it to say 23, so again we use parentheses here, which means multiplication. So y equals 2 times 3, which is 6. Okay. That's my y value, and so my ordered pair is 3, 6. And again, what that means is that's my point of intersection. If I were to have graphed 20x minus 7y equals 18 and y equals 2x, that is the point of intersection. Okay, we have one final example. Again, we're going to increase the complexity of what y is equal to. Again, focusing on specific substitution problems where we have y already solved for. So y in this situation is equal to x plus 2. Again, increasing the complexity, just making it a little bit more interesting. So y is equal to x plus 2. Because y is not an integer value yet, I'm going to go ahead and put a cloud. That's the best kind of cloud I can make around that, so I know to come back to this. I need to come back to that y equals x plus 2 at the end of the problem. Okay, I know that I'm going to substitute, so this value right here is going to come out. So I'm going to work with the top equation. So the x is going to stay plus 3. Instead of y this time, I'm going to put a bigger parentheses equals 26. Now the reason I'm putting a bigger parentheses is because I know already what's going to go inside that parentheses. I'm going to substitute the value of y, which is x plus 2. X plus 2. So I want to give myself enough space to be able to do that. Now, there should be a little light bulb going off, a little lightning bolt in your head that's saying, oh my God, that looks like distribution. It is. So I'm just going to go ahead and draw the little distribution lines in there for when we get there. And now I'm going to go through and simplify the problem. X stays exactly the same. Plus, now I'm multiplying. 3 times x is 3x. Following my distribution lines, 3 times 2 is positive 6. And that is equal to 26. Okay. Now I'm going to combine like terms. I have an x and a 3x. So if I have 1x already and I'm adding 3 x's to that, all together I have 4 x's. The plus 6 comes down, and that's equal to 26. Now this is a very simple two-step equation that I can solve really easily by working backwards. I'm going to subtract 6 from both sides. The 6 and the negative 6 cancel. 4x comes down. Getting a little cramped for space, so I'm going to just try to fit it in. 26 take away 6 is 20. And now to get rid of the 4, we're going to divide. And when I divide 20 by 4, I'm getting x is equal to 5, which is now one confirmed value. X is 5. I can put that into my word pair. Okay. Now, last step again, I have a confirmed value for x. I need to go back and find my value for y by plugging 5 into this y equals equation. So y is equal to, instead of x, I'm putting in the value of 5 plus 2. So y is equal to 7. Okay. And then because that's our second confirmed value, I can plug that in. Y is 7. Y is 7. Okay. And that is substitution, basic substitution at that, because all of our values were already set up so that we had y equal to something. So substitution definitely gets more complex than this, but for our focus today, already having y solved for and then substituting that into the other equations, this is as complex as it's going to get.